This is lesson 1.3, Applications of Systems of Linear Equations. One of the things that I really appreciate about this book, and we're gonna do these lessons in each chapter, is that each chapter ends with a section on applications of what we've learned in that chapter. As a math teacher, I'm often asked, when am I ever going to need this? How am I ever going to use this in my life? You know, I think about imaginary numbers and some of those other things that really do have actual value and purpose in certain industries. And so I think this idea of kind of ending our chapters looking at some ways that these are actually being used in certain industries or in certain ways is certainly important, and just kind of opens our eyes to really seeing how the concepts that we are learning are actually meaningful and actually have purpose. So we're going to look at two different applications here. We're going to look at polynomial curve fitting, which I admit, I agree, is going to definitely feel more mathematical, but definitely has its place and its purpose outside of just academic mathematics. The other one we're going to look at, though, which I think is far more fascinating, is networks and how we can use systems of equations to model and solve different networks. There's a third application in the book that we're not going to do, and it deals with electrical systems. It's actually a very fascinating, very pertinent application. It's probably, honestly, one of equally as important as the idea of networks, or used as often as networks. But I've chosen not to do that or look at that one because it's very technical. In terms of dealing with the ohms and amperes and resistance and all that kind of stuff that's related to electrical engineering, I didn't want the technical aspects of that application to cause us to lose sight of just this idea of how we can use systems. So if you're interested in that, if you have any kind of interest in electrical systems, I would encourage you to look at the book and look at the examples that they have for that. They really are quite interesting. But we're just going to stick to these two for this lesson and in terms of what I would want you to kind of walk away with from this chapter. So let's go ahead and let's jump into the first one, which is polynomial curve fitting. So one of the things to mention here, start off by saying, is that when we talk about polynomial curve fitting, what we're talking about is given a certain number of points, finding the curve that passes through all of those points. This isn't like finding a curve of best fit or anything like that. It's specifically finding the curve that will pass through each of those points. So one of the caveats here is that the degree of the polynomial has to be one less than the number of points. So if I have 4 points, I can find a polynomial of degree 3 or a cubic function. If I have 7 points, I can find a polynomial of degree 6 and so on. So that's kind of one big caveat we need to have as we approach this. So I'm just going to do one example of this just to give you an idea of how this works. So in this case, we're going to find a quadratic equation, a polynomial of degree 2, given the 3 points, -2, 0, 1, -3, and 3, 15. Now, as we kind of set this up, I want you to keep in mind and kind of see the bigger picture here of what we're doing. So if you think about a quadratic equation, we think of it often as ax squared plus bx plus c. We might even think of it as equaling 0 and using the quadratic equation or factoring or things like that to solve it. I'm going to turn it around, though, a little bit. I'm going to write it in this form. I'm going to write it a0 plus a1x plus a2x squared. And the reason I want to write it this way is if we were to, for example, want to extend this idea to a cubic function, a quartic function, or anything higher, the idea is that I would just keep adding, a3x cubed plus a4x to the fourth, and so on. So I could make this as large of a polynomial as I wanted to. So as I added more points, I would just simply be adding more terms to my polynomial. Okay, so the idea is that really what we need to do here in order to find this quadratic is we need to figure out what is a0, a1, and a2. Well, we're going to get those from our 3 points that we're given. So we're going to set up 3 equations using that. So for example, obviously we've got our x and our p of x in our points. So in this case, if x is negative 2, I can think of p of negative 2 as simply being a0 plus negative 2 times a1 plus negative 2 squared is 4, a2, which is equal to p of x, or 0. And then likewise, I can take the other 2 points and set up those equations. So for the point 1, negative 3, I would get the point a0 plus a1 plus a2 equals negative 3. And then for the third point, I'd have a0, or the third equation, excuse me, I'd have a0 plus 3a1 plus 9a2 equals 15. So as I look at these three equations, that's going to give me the system that I need to now solve this. So just as we did in the last lesson, looking at that Gauss-Jordan elimination method with matrices, we're going to do the same thing here. So I'm going to take those three equations now and simply set up a augmented matrix: 1, negative 2, 4, 0, 1, 1, 1, negative 3, and 1, 3, 9, 15. Now, I'm not going to go through all of the steps of solving this, but bottom line is we would do exactly what we did in the last lesson. We would just use the Gauss-Jordan elimination method to solve this. And if we did that, if we went through all those steps, we'd end up with a matrix 1, 0, 0, negative 6, 0, 1, 0, 1, and 0, 0, 1, 2. Which means that a0 is negative 6, a1 is 1, and a2 is 2. And so my equation, my quadratic that goes through these 3 points up here, that quadratic, is p of x equals negative 6 plus x plus 2x squared. That's it. That's all you have to do. So again, obviously, if we were to add more points, if I added a fourth point, I would just have another term in each of my equations. I'd have 4 equations. I'd have a 4 by 4, or excuse me, a 4 by 5 matrix that I'd have to solve, and so on. So it just makes the matrix bigger and bigger, more to solve. But ultimately, it's the same process of just getting down to that final matrix that gives me those solutions. I plug them back in, and I've got my equation. So that's just one application where we can use matrices and that idea of Gauss-Jordan elimination in order to, in this case, find a polynomial that goes through the points that are given. Well, let's move on to our next and what I think is a more interesting application, and that is network analysis. So here, if you know what a network is, and I'm not sure what happened to my picture there, but this should, you know what, we're gonna fix this real quick. Bear with me here for a minute, just so it's not too confusing here. So this should really be just a line that's passing through like that. There we go. Okay, so if you know networks are just systems where you have a node and you have paths and they're all connected. There's a really famous network problem is called the Bridges of Königsberg. It's a problem where supposedly back in I guess what I'd call old world Germany back in the day, there's a park that has, let's see if we can get this picture right here, that has kind of a river flowing through it and an island or two. And there's bridges that connect in this park in various ways. And I can't remember the drawing exactly. I think there were maybe 2 bridges like this and maybe some bridges like this. I think this was the picture. And the question is, you know, the idea was that people would go on a Sunday afternoon and they would picnic in this park, and then they'd spend the afternoon walking across all of these various bridges. And the question is, can you walk across all of the bridges exactly once without retracing your path? And the answer, without getting into too much detail, is no. But basically, this is a network problem where we could set this up as a network and use some properties of networks in order to solve that. Well, another way that networks are used are to look at flow, whether it's flow of people, flow of materials, shipping routes, anything like that. So what we've got is we're going to use, again, a matrix to analyze a network where the total inflow to a node has to equal the total outflow for the node. So for example, think of an airline where we've got hundreds of planes flying into an airport, dropping off passengers, and those passengers all have to then leave the airport. So if I think of a node as an airport, so if this node represents an airport, then it's the flow coming in are people flying into the airport, and the flow going out could be people not only flying out of the airport, but maybe just leaving the airport. They've reached their destination, things like that. And so setting up a system, if we know certain information, as this gets more and more complex, we could actually use this to maybe look at efficiencies. What's the best way to route our airplanes, to plan our schedules, all of those sorts of things in order to create the most efficient, profitable network for our airline system. So very simply, in this case, because we have 5 nodes, we're going to end up with 5 equations, because for each of these nodes, we're going to set up an equation that simply represents the total sum, the total net sum, so to speak, of inflow and outflow having to equal 0. Okay. So for example, and I'm gonna let me just kind of erase a bunch of this stuff so that it's not quite so cluttered up in here. So let's take, for example, let's call this just node 1, 2, 3, 4, and 5. And that we can kind of, as we're going to write our equations, we can kind of refer to those. So if I look at node 1, for example, I have 20, whatever it might be, flowing into 1. And then I've got a quantity of x1 and x2 flowing out of node 1. So remembering that the inflow has to equal the outflow. So in this case, the outflow, x1 plus x2, has to equal the inflow of 20. So x1 plus x2 has to equal 20. That's what we get at node 1. And as we continue through, we're just going to come up with equations for each of these nodes. So looking at node 2, here we have an inflow of x4, we have an outflow of x3 and of 20. So in this case, an outflow of x3, I'm going to think of that as a negative, x4 as a positive, and then equals an outflow of 20. So on the left side, just kind of explain what I'm doing here. On the left side, I'm thinking of inflow as being positive, outflow as being negative. On the right side, I'm thinking of inflow as being positive and outflow as being positive and inflow as being negative. Okay. So for number 3, for that node, we've got an x2 coming in, we've got an x3 coming in, and then going out, we have a 10 and a 10. So that's going to be a total of 20 outflow. For 4, we've got an inflow of x1 and 10, and an outflow of x5. So we've got an x1 minus an x5 equals an equals an inflow of 10. So then that's a negative 10. And then for number 5, we've got an inflow of x5. We've got an outflow, of x4, so that's a negative. And then we've got an inflow of 10, which is going to make that a negative 10 on the right side. So now that I've got that, I've got my 5 equations, and we can go ahead and set up our system. So from the first equation, we have 1, 1, 0, 0, 0, 20, and then 0, 0, negative 1, 1, 0, 20, 0, 1, 1, 0, 0, 20, let's see, 1, 0, 0, 0, negative 1, negative 10, and 0, 0, 0, negative 1, 1, and negative 10. And let me make a little bit better of a bracket here that fits this. So there's our augmented matrix that we can solve. Now, obviously 5 variables, 5 unknowns, but if you look at this, there's actually not a lot of work to do this if we were to use the Gauss-Jordan elimination, which again, I'm not going to go through, but if we were to use that and get that down to that row-reduced echelon form, in this case, what happens is a little bit different than what we had before. If I were to solve this, I'd have a 1, 0, 0, negative 1, negative 10, 0, 1, 0, 0, 1, 30, 0, 0, 1, 0, negative 1, negative 10, 0, 0, 0, 1, negative 1, negative 10, and then the last row would be all zeros. Now, you should have run across this at some point in the homework, and we did hit a problem in the first, I think it was the first or second lesson, where we had infinite solutions, infinitely many solutions. But when you get a matrix like this, what's happening is there's an infinite number of solutions because we didn't get this down to a complete row of, or column, diagonal, I should say, of ones here. Because of that 0, and because we basically have all zeros in this bottom row, it's telling us that there are infinitely many solutions. So in this case, there isn't actually one solution to this network. But let me kind of go a little bit deeper with this and think about another way to think about what we do have in this matrix. So in this matrix then, I'm going to let T equal x5. Okay. So if I look at my first, so think about this. This is like the x1, this is x5, right? That's x1, x2, x3, x4, x5. And then we have what the values were on the right side. So if I let T equal x5, what I end up with then is in that first row, I have x1 minus T equals negative 10. In the second row, I have x2 plus T equals 30. In the third row, I have x3 minus T equals negative 10. And then x4 minus T equals negative 10. And then obviously I'm going to rewrite this just so we can kind of see the whole progression here, but x5 then is just simply T. So if I solve now for x1 through x5, I'm going to get x1 equals T minus 10, x2 equals negative T plus 30, x3 equals T minus 10, x4 equals T minus 10, and x5 equals, again, just T. So while I don't have a specific solution to this network, what I do have is a situation where if I know T, in other words, if I know x5 or I assign a value to x5, I can basically get all of the other values. So maybe this is a situation where as I'm looking at this system, this network, you know, this is kind of the linchpin to this whole network is this x5. So if I make x5 50, that's going to trigger all of the other values in this network. And so, you know, maybe I'm concerned about certain constraints. Maybe I can't have certain paths be more than 30 or less than 10 or anything like that. So I now have a system of equations here that I can very easily analyze and look at based on what I do with this x5 value. So while it's not, you know, a lost cause that we got this infinitely many solutions, what it does is it just presents a situation where, well, there isn't a solution, but it's going to depend on what we do here in this path that's going to determine the entire rest of the network. Other networks will work out where, you know, you will get a solution where it has to be this for each value. This just happens to be a little bit different. But when that happens, I want you to think about, you know, how we use that information, that again, it's not a lost cause, and we're not just going to stop by saying, well, it's just infinitely many solutions and now we're done. We don't have to think about it. Well, what does that infinitely many solutions mean? It means that I've got a system that I can analyze and look at and see the interdependence. Even the fact that, for example, we've got x1, x3, and x4 are all the same. So no matter what value I plug in for x5, those three paths are always going to be the same. So maybe here, along with x5 kind of being that linchpin, maybe I'm really concerned about what's happening in x2 because that's kind of the oddball out. So hopefully you kind of get the idea there, but bottom line is, again, this is another example how we can take a network and by looking at the equations at each of those nodes, we can set up that system and either solve to get a very specific solution for that network, or in our case, get a system, another system that we can look at and analyze based on what's happening in certain parts of that network. So that's it for this lesson. Again, I want to remind you that, if you are interested in kind of seeing other applications, they are in the section of 1.3 in the book, and certainly there's the electrical application there that you can look at if interested. Other than that, I will see you in the next lesson.